Good morning, everyone. I'm Leona from Wizlogix, the host for today's WizConnect webinar. Wizlogix has been in the business for PCB layout design, fabrication, component kitting, and assembly services for 20 years. We are glad to have our internal trainer, Ms. Suriani, who is as well our PCB design engineer with 14 years of experience in the industry, to share on how you can minimize the risk of project delays and costs, as well as to streamline the PCB production process with Gerber techniques. I will now pass the time to our speaker. Sue, please.
A very good morning again, everyone. I am Suriani, the IPC certified designer, as well as the internal trainer for Wizlogix. Welcome to today's webinar session. Here, I will be sharing some tips on Gerber techniques that we can practice to streamline the PCB production process. So before we begin, let's take a look at what is Gerber. So Gerber is essentially an open ASCII vector format for printed circuit board designs. So Gerber is actually the industry standard to describe images for several layers, such as the copper layers, solder mask layers, base mask layers, silkscreen layers. So if you were to open up your Gerber data in a notepad or even a WordPad, you can see the codes here on the right. Okay, the Gerber data will be coded in such a way that it conforms to the ASCII vector format. So you can see several items stated here, and the ADD here, it is referring to the aperture embedded into the Gerber data, and followed by the other information stated here. As for the drill data, as what you can see here, okay, drill data format are actually also embedded in the ASCII vector format, and the format that we are using is actually the Epsilon 2. This is the latest format for drill data. So what you see here will be the coded data for the ASCII under drill data. So you can see the drill size for the design that you are doing, and stated here the hole size as well as the other parameters relating to the drill holes. Okay, Gerbers are actually in the RS274X format. This is the latest format for Gerber, and this standard format allows the information to be contained in a single file. So the file will contain embedded items like your unit and data, as well as aperture definitions. So you don't have to have separate files for apertures as well as Gerber data. And then RS274X also allows special polygon definitions. So you can actually define items or shapes other than your regular square, circle, or even triangle. You can have odd angle polygons embedded into your Gerber data. And RS274X also allows multiple layers to be contained in a single file. So it helps you in your data or file management. So RS274X is actually an extension of the previous or the older version, which is RS274D. So if you require more information, you can actually look up this website or some other websites regarding RS274X extended version for Gerber data. So basically, RS274X allows the PCB designer to define essential blocks of codes and embedded format or embedded information in a single file. So you don't have to maintain many files or subsidiary files for a set of Gerber files or Gerber data. Okay, so how are Gerber data or Gerber information used? Okay, in the fabrication or manufacturing process, the Gerber data or the Gerber information is transformed to photo tools, and they are being printed out using special printers like the one I've shown here. Okay, the Gerber image will then be transferred to these films in a black and white format. So this is like how the film photography works. Cameras use a film to actually capture image, and then you use these films to develop into physical paper photos. So the concept is quite similar for this photo tools film. And then for the copper layers, which includes the internal and external signal layers. So you can see here, this is typically how an external signal layer will look like. And this is how a typical internal layer signal will look like. So you can see traces denoted by the lines here, as well as pads or copper areas denoted by the black areas. So whatever that you see on your CAD software, or whatever that you include in your layout design in your CAD software, you will be able to see in the Gerber data. And then for plane layers, okay, this is a positive view of positive format of the plane layers. Here you can see black areas more than white areas. So what this conforms to is actually the black areas are where you would want copper to exist, and white areas will be where copper will be removed. Okay, this is the positive format for copper plane layers. As for the negative version or the negative format, okay, this is what you will typically see, whereby the red areas, and this is the view from the Gerber software, one of the Gerber software. So the areas here shown in black are the areas where you would want copper to exist, and the red areas, or the areas that are denoted in color, will be the areas that will have copper removed by chemical etching. Okay. And then we have next is our solder mask layers. Solder mask layers are actually defined by the solder mask openings or the black areas. Okay, solder mask layers involves the top and bottom because we have the top and bottom layer. So black areas are representing the areas where you would not want to see solder mask coating. So that's how you will see in this picture here. So these black areas will actually transform into these areas where copper will be exposed. So those areas in white will be where you want solder mask coating or solder mask covering. So if your solder mask is green, you will see them in this manner. So this is how we translate the images on the solder mask layers to the actual physical PCB board with the solder mask coating. So there are several solder mask colors out available in the market. There are several other colors like orange, purple, red, blue, and even black. Okay, but green is the most common colors used by a lot of companies and in the industry. Okay, so solder mask openings include things such as your copper pads for SMT and as well as through-hole components, and all sorts of holes such as your mounting hole, screw hole, alignment, and even tooling holes. So these holes that do not require any solder mask covering will have the solder mask opening areas in black shown in your Gerber data here. So white areas, like I said earlier, where white areas will be denoting where your solder mask coating will be covering. And then for paste mask layers, they are similar to what you will see on your solder mask layers, but so the paste mask layers also include your top and bottom layer. You will only see openings for copper pads for SMT components. Okay, this layer will also be used as a stencil guide for solder paste application for SMT components. And then we have the silkscreen layers. So the silkscreen layers, also the top and bottom silkscreen layers, you will see legends, tags, ref desk or reference designators, lines, any logo or any cosmetic application that you require on your PCB board. And then we have the drill data. Okay, for drill data, on the Gerber information itself, you will see circle dots, and these are indication of the location and size of the drill or holes used in the PCB layout. So over at the manufacturing side, this drill data info will be loaded into the drilling machine for the drilling process. Okay, so besides all these layers that I've shown here, we also have another layer or another drawing that we call fabrication drawing. So this layer or this drawing will include any information pertaining to the manufacturing process. You can include things like your drill table, which is denoted here, where you can specify the drill type, whether it's a plated hole, stated here, or a non-plated hole, the drill size, the hole size, the quantity, the symbol, and even the tolerance. As well as the layer stack up here, we can actually include any layer stack up or material information inside this fabrication drawing as well. And then you also have the dimension of the project or the PCB layout itself. We can also include other information related to the manufacturing process, like your surface finish, the materials to be used, even the solmas and silk color. So any other information pertaining to the fabrication process is crucial to be added into the fabrication drawing. So that means you don't have to come up with a separate document to entail all the requirements of the PCB layout or the PCB product on a separate file, like using Excel format or even Word document. So everything is contained into one format, which is your Gerber data, which it will be translated to the vendors or to the assembly house for fabrication and assembly. So this is actually the format that we design engineers use in-house when Wizlogix designs engineers perform layout works in-house. Okay, so we have the Wizlogix logo here as well as all the other information crucial to the fabrication process included in this drawing. So other than the fabrication drawing or the fabrication process, we also include drawings for assembly. So for assembly, normally or most of the time, assembly is done by automation or by machines. So machines will actually load up and do a pick and place of the components onto the PCB layout or PCB board using the AOI or Automated Optical Inspection Guide. So usually this assembly drawing will be used to check on the component loading, component orientation, or if there's any issues or any discrepancies between the location as well as the data in the Gerber. So this assembly guide will be useful if there's any errors or any faults found during assembly process itself. Okay, so for Gerber, besides generating from your CAD software, okay, how do you ensure that the Gerber files that you have generated or you have created are correct? So we usually use a Gerber viewer to view and sometimes edit items like your solmas expansion or even silk screen clipping if necessary, and if there's any additional data, text lines or shapes required. So most of the time, fabrication house or manufacturing house will actually use Gerber viewer on their end to actually check and inspect that our Gerber data or the Gerber data that is passed to them conforms to their manufacturing capabilities, as well as no crucial or no critical errors found. So for us at Wizlogix, we are using this software, CAM350, to actually open up, view, and edit Gerbers if necessary, or feedback items that can actually interrupt or be a potential problem in the manufacturing process. When we talk about Gerber, we also talk about apertures. So apertures in Gerber are actually data or items. So all the data and items are actually defined by apertures. Apertures are actually encrypted codes that contains information. So this information are actually shown in this table format here. Okay, all apertures will have a decode number to actually represent the listing of the apertures. And each aperture will have their own specific shape, size, and their own parameters. And then every item in aperture or every item in the Gerber data will be made up of a combination of decodes. So decodes can exist as a flash or line or even a polygon. So flash can be of any regular shape, like your rounds, square, rectangle, triangle, oblong, or oval, and diamond. So these are all your regular shapes, as long as it's a filled closed shape. As for line is actually represented by copper traces and made up of many decodes joined together to form a line. So your line trace or your trace routing in the Gerber data itself is actually made up of many decodes, like your round shape to actually come up with a trace line. And then polygon is actually a custom shape with special decode definition, unlike your flash or line. So if you have the time, do open up your Gerber maybe in the software, in your GC Preview or even Altium or even UMIT software. Do open up and take a look at the apertures, and you can see that the listing of the decodes here actually defines your Gerber data. Okay, So next, I will talk about Gerber techniques, how we can make improvements on our PCB layout to actually alleviate potential manufacturing issues during and after the fabrication stage. So these improvements help to reduce risk during the copper removal by chemical etching. So in the manufacturing stage, right, copper exists in a roll format or roll foil format. So this format is like how you will see your aluminum foil in your house. So this roll format will require the copper to be removed for areas that you do not require trace or even copper areas. So these copper areas will be removed by chemical. So removing by chemical, it's a more mass process and is mostly used by the manufacturing house. So issues such as under etching, that means not enough copper removal, or over etching, that means too much copper removal, and undercut will also happen during the chemical etching stage. And then acid traps and bottlenecks are also some of the risks involved by the chemical etching for copper removal. So over here, the picture on the top right shows the PCB board with under etching. That means you can see that some areas still have unfinished copper removal. Okay, those that are in matte color, matte brown color, will be where your copper is removed, and those in the shiny copper color will be where you want traces or copper. So you can see that the areas circled in green are areas where copper etching or copper removal by chemical etching is not finished. That means there are still some sliver of copper remaining, which cause this, for example, this signal and this signal to short. So you can have potential issues such as short and open net when copper etching is not done properly, and there will be risks involved. And then you can see here an example of an undercut. So the too much copper is removed at the middle of the height of the copper based on the thickness. And then here we have under etching also. That means you have coppers where you do not need them, but they are actually left there by the chemical etching process. So ideally, what we would want to get is something like the one on the bottom right picture here. But you can see at the edges here, there are some zigzag lines or some uneven lines. So these are actually some of the risks involved when copper is removed by chemical etching. Okay, so what are the advantages of implementing Gerber techniques and check? So what we can help is to actually minimize feedbacks from your manufacturer on faults or correction to be done on the Gerber. So whenever you have feedbacks, right, it will take time. So time can be translated into you need more effort to correct these mistakes and faults, as well as you delay your schedule. It means you need more time to make the corrections, and then after that you need to regenerate Gerber, do another check, and then send to them. So all this going back and forth on the feedbacks and on the corrections will actually delay your schedule. So when you delay schedule, money is involved. So let's say, for example, you are making products for a customer. So of course, customer wants fast and wants on-time delivery. So when anything is delayed, more money is to be involved to compensate for the time lost. Okay, so other advantages includes to ensuring that the Gerber data conforms to your manufacturing capability of the fabrication house. Okay, each manufacturer will have their own set of manufacturing guidelines or capability that they can perform. So each manufacturer will also have trace width and spacing clearance specification, and what is the minimum that they can conform to in order to produce a particular set of Gerber data into a PCB board. So do check with your manufacturer or your fabrication house on their manufacturing capability, as well as what is the limit that they can accept for any PCB or Gerber data. And then Gerber techniques and checks also actually help to increase yield. So therefore, you will lower costs. That means whatever that you send to the fab house or the manufacturing house will be able to be produced or will be able to be fabricated Therefore, there's no mistakes, there's no loss of yield, and you do not have to pay extra for any loss of yield. And then you can also help to reduce EMI, AMC, or even crosstalk issues. And these are relating to any antenna or dangling lines. Okay, any antenna or dangling lines will translate to dangling copper. So this will not be good for any EMI, AMC if you have any critical signals on your PCB layout. And then this will, for ground reference, checking and implementing Gerber techniques to also ensure or help to remind you to have the proper ground reference for critical signals. And then do bear in mind that clearance for diffusion pairs and impedance matching is also very critical. And these are actually implemented during the design layout. So during the Gerber techniques and check, do ensure that all these are actually met in order to help you to reduce EMI, EMC, or even crosstalk issues. Okay, so what are the Gerber techniques for design improvement? So here over the next few slides, I will show you some do's and don'ts during design outline or design works and how we can improve them. So some of them you have seen in your daily work or in your layout design, and some of them, although it's still manufacturable, but we do try to avoid them to actually improve manufacturing capability, and of course, at the end of the day, improve time as well as money. Okay, first will be the routing stage. Okay, I will be going through some pictures on routing. Okay, first and foremost, we do not practice routing in between component pads. Again, this is especially critical for two-pin discrete components. Let's say, for example, your capacitor, your resistor, diodes, inductor. So as long as they are SMD and they are discretes, and then we try to avoid routing in between them. So, like I mentioned, we do not route in between component pads. So the picture on the left here is the before and after. That means the implementation or the improvement done is in the after picture. So in your layout, right, when you route in between discrete components, okay, what will happen is that you will reduce the clearance or the spacing in between the pads as well as the copper trays. So when you reduce the clearance, it makes it harder for your manufacturer to fabricate and to ensure that the spacing is met. And another reason why we do not route in between component pads, especially for a discrete component, is because most of the time, discrete components are made up of several packages. Okay, they are usually packaged in either plastic, ceramic, or aluminum body. So if let's say your discrete component is using the ceramic or plastic body, it's still okay. But if it's using aluminum or any metal or any conductive material for its package, then it will be a potential issue for short, especially when the component is loaded onto this area, and then you have a trace running in between. And then also solder mask or PCB board, after many rounds or many years of use, there will be wear and tear on the solder mask area, especially on where components are loaded in. So potentially solder mask can be removed either by years of use or by the heat generated by the component itself. So exposing the trace here, the copper trace here at the center. So you can definitely we definitely want to avoid this kind of scenario. So what we do is normally we try to avoid and route out of the component itself. So this is a good practice to actually keep in or bear in mind when we do routing on discrete components. Quick question: which of the following routing method is not recommended? Okay, we have A, which is your 90-degree corners. B, we have 2 of 45-degree corners, which is noted by this corner here. And then C, we have arc corners. And then D, we have sharp corners. So this is like a 45 sharp corner. So which of the following routing method is not recommended? So D, routing at this sharp corner is not recommended. And most of the time, we do not want to practice this kind of routing. Okay, what will happen is that there will be an issue called acid trap. Okay, what will happen is that acid from the chemical removal stage will be trapped in this area and will still be left behind even after the chemical washing or even after the whole PCB board is fabricated. So the issue of acid trap is very highly possible in this routing method D. As for routing at 90-degree corner, although not very much preferred, it's still a practice in some PCB layout today. This is not a manufacturing fault, but during copper removal stage, what will happen is that at the corner here, at the outer corner here, let me check. Okay, at this corner here, at the outer corner here, what will happen is that potentially the copper will be over etched. That means too much copper removed on this outer edge here, which will result in a thinner than what is required, thinner width than what is required. So you can have the normal trace here, and then you have a very thin trace here with and then back to normal trace here. So this is not a very good chemical removal stage if you end up with a over etching at the corner here. As well as on this inner corner here, what will happen is that you can end up with an under etch whereby too little copper removed. So you end up with something like this. So although you get the same trace width as the one on the this axis or this axis, but because it deviates from your actual design, so it's not a good practice. Okay. So if let's say, just imagine if you have any other trace running here, this under etching will actually make or allow this end of the copper to touch another trace if you have any trace here or any other series of traces here or buses. So that's a potential manufacturing problem. Okay, as for if let's say you do require this kind of routing whereby you need to go from this vertical line to horizontal line, what is a good practice is actually to form two 45-degree corner like the one here. So you do a corner here and another corner here. You still end up at the same path, but you just need to add two corners here and you can get to the same path but with a better method. So in manufacturing aspect, the copper removal stage is easy to control chemically using this 45-degree corner. So same goes for your arc corners. And these arc corners are also traveling the same path from the vertical line to the horizontal line. But usually for arc corners or for arc routing, it's usually used for length or even impedance matching purposes. So technically, we will normally just go with the 45-degree corner because it's easier to route, touch up, and change your kind of routing if, let's say, there's a design need. Okay. So, like I mentioned before, we do try to avoid routing 45-degree angles. So we normally will make changes to any 45-degree angle to actually improve the manufacturing capability or the manufacturing outcome. So you can see the before picture, you can see 90-degree here, and you can see some sort of a weird angle here. So when we change and improve it, it becomes much more better, and as well as it's easier to manufacture in this stage. And then the picture on the right, you can see a sharp angle here, as well as the one here. And when we change it, this is how we improve the layout design. And then we have the sharp corner here. When we change or we improve the design, it become like this. Okay, as for this kind of routing, okay, we call it steps. Okay, to ensure that we have enough copper flow. Okay, usually copper flow is for grounding or ground reference purpose. So we try to improve to allow a better copper flow for ground, as well as to remove any jagged lines, because it's not pleasing to the eye, and as well as being a little bit more harder for the manufacturing to control the flow of the chemical etch. Okay, we do remove fine copper or antenna, like I mentioned before, Fine copper and antenna are actually dangling lines. They can also be a point of AMI or even crosstalk issue. So we try to remove any fine copper and antenna as well as isolated copper. And for test point, if let's say we have this kind of differential pair routing or even this kind of routing with thick traces, which will require 1, 2, 3, 3 type of capacitors and a pair of test points. Okay, we try to improve the location of the test point so that it will sit along the trace routing instead of being a stub like this picture here. And then we have the issue of missing connection from trace to copper pad. Okay, even though in this picture, the pad and the trace is somehow connected, but we will try to improve to make sure that it has a proper endpoint on the pad and connection to the next via. As for T-junction, here we can see 90-degree junction here. So if you cannot avoid this kind of 90-degree junction or 90-degree routing due to length matching or differential pair requirement, what we can do is just add a little bit of trace here to make it like a chamfer or a 45-degree kind of routing. Okay, so just a little bit of touch up will go a long way. And then we have here the issue of trace routing exposed at solder mask or the white area for the solder mask opening. So if let's say you require a solder mask opening or exposed copper on this area or this wagon wheel hole, as we normally label it, what will happen is that trace copper, when routed in this angle, will get exposed. So exposed copper will actually be not good for any reliability issue, as well as if there's any metal bracket or any screw hole to be mounted here, it will actually cause a short to this signal. So we will reroute and avoid the exposed solder mask opening area. Okay, so I've covered some of the techniques for routing. Next, I will touch on the plain connections. So there are several things that we can do to improve the plain connections. Okay, if there's any copper voids on large copper area, we will remove them. This could be for an accidental addition of a copper void. Okay, unless the design require copper voids, we do not practice adding copper voids on large copper area, because copper areas are normally used for reference, either power or ground. So we try not to have any missing or any voids on large copper areas. And then we also have issues on improper copper fill or fine gaps. You can see that there's a sliver of black line here, and this indicates that there's a gap between this copper area to this copper line or even trace line. So we do a little bit of touch up to actually match or even join these two areas together so that you will not have the very thin line here. And then uneven copper to copper separation. If let's say on your ground plane or on your copper plane for power, you have several power using the same on the same plane. So what we do is we will have special copper shapes or copper areas for each individual copper or power dedicated to that power supply. So for that particular power plane, we try to have an even copper to copper separation so that we have the proper reference, as well as manufacturing wise, it's easier for them to manufacture if you have the even copper to copper separation. So it's hard to control if you have some areas bigger copper separation, let's say for example 100 mils separation, and then this side will be 50 mils separation. So unless specified for your design layout, we normally maintain an even copper to copper separation. So in the case whereby you're using vias and you have a lot of vias for ground stitching purposes, and some of the vias actually protrude out of the copper area, try to shift your via into the copper area, or if it's not possible, try to actually shift some of the traces to allow the copper to to cover your via. So if there's any protruding out, it will not be easy for the manufacturer to control this particular small area versus this big area when you have via protruding out of your proper area. Okay, so there's another issue here for bottleneck areas caused by the position of your vias in regards to the copper plane. So this will cause potential copper plane flow issue. So for example, if you have a plane here and it's for example, 1 volt power flow. So because of this via that is actually protruding into the copper plane area, so you have a bottleneck here and the rest of the copper plane has a bigger width, but in this area, the power flow is only within this short bottleneck here. So that could cause some power distribution issues or any other power related issues. So what we normally do is we try to improve this kind of bottlenecks by either removing the via and locate it at a different place, such as the one in this picture here, or you can actually increase the width, the total width of this plane if it's possible. Okay, it also depends on your layout requirement. And then for mouse bites, okay, mouse bites are essentially pieces of holes, a few holes actually drilled onto the edges of the board to allow you to do a manual separation of your PCB board, so that your PCB board can be manufactured in a panel mode, and then when it arrives to you, you can actually dismantle or break them off and use them as required. So this is especially useful for boards that are smaller in size, and then to increase your output or reduce costs, you can actually panel several designs together into one panel. So you can actually reduce costs as well as have the boards arrive to you, and you can actually break them off and use as required. So for copper protruding into mouse bite holes, because these boards will be manually broke off at your end. So if let's say we have copper protruding or even at the copper, at the mouse bite lines, right? What will happen is that when you break them off, copper will be exposed on this end. So when we have copper exposed, over time, the exposed copper, as well as the exposed material, will absorb moisture. So over time, it could be years, months, moisture will seep into the board and cause expansion or warpage on this particular area, and then it will then spread to other parts of your board. So we want to we want to avoid this kind of situation. So what we'll do is that we will pull back the copper on this mouse bite regions. And then there are some things that, or some practices that we do for thermal ties on plated through hole. So for plated through hole, normally we will do thermal tie instead of flat connection. So this is an example of a plated through hole for a bulk component, for example, your bulk capacitor, bulk inductor. And then this is a sample for a thermal tie on your mounting hole or even screw hole that requires copper. Okay. And same thing for SMD pads. We do not practice flat connection. Instead, we will do thermal connection, thermal tie, sorry. So for example, if let's say we do a flat connection, what will happen is that heat during the wave soldering process will be dissipated easily through the rest of the copper area and cause a cold solder for soldering. So what will happen is that you will not get a good solder joint for your component for these two pads. So heat will be travel faster out of these pads versus your thermal tie. Okay. So we will not want to have any cold solder joint or any solder issues on any SMD components. So we will normally use thermal ties instead of flat connection. But for via, it has the opposite effect. Vias, they are meant for toggling connections from one layer to another. And because the vias are relatively smaller in size, so we do not worry about heat or transfer loss. So generally vias, we use flat connection instead of thermal ply. And you can see that the thermal ply is actually so small that it does not have much effect versus your flat connection. Okay, so for unconnected or non-functional pads in internal layers, we normally will remove them. And why we remove them is actually to improve the via capacitance, because any via used on the PCB board will have some form of capacitance. And it also improves the reliability, spacing, and yield for that particular board for the via, so that your via can last longer without any breakage in the via itself. Okay. So for solder mask, we do ensure that all copper pads will have its specific solder mask opening. So if let's say there are any missing solder mask opening, will need to open them out. Only for special cases where these solder mask openings are not required by your layout design or by the specifications of the design, then we will not have this kind of practice. And then solder mask or paste mask opening should be equal or slightly bigger than your copper pad. Okay, rarely do we perform solder mask opening smaller than your copper pad. And then for fiducial points, if fiducial pads are actually markers on the PCB layout used mainly for the purpose of automated assembly. Okay, so the pick and place machine, by the use of the AOI, automated optical guide, automated optical inspection guide, use these fiducial marks to actually align and place components in the proper orientation as well as the correct X and Y location on the board. So in the market right now, or most of the time, we practice fiducial copper pad of 1 mm with a solder mask opening of 2 mm. So because of these specifications, try not to place any fiducial pad close to any mounting hole or any copper areas, because it will expose them, and it's harder for the pick and place machine to actually detect these fiducial marks or fiducial points as a guide for your automated assembly. And next, for silk screen. So silk screen legends, be it ref desks, tags, or any traces, we do not practice solder mask overlapping on solder mask opening areas. So any solder mask with silk screen overlapping will be removed. So in this case, if you have this particular ref desk J10 and this indication overlapping your solder mask, what the fab house or the manufacturing side will do is that it will remove all these indication or any legends that fall on solder mask. So you will have missing legends in this case. So what we'll normally do is we will manually move all these ref desks out of the solder mask areas and put them in an appropriate manner. So always align your legend or your ref desk to its associated component. So you can actually practice in such a way. Okay, do arrange legends in a neat fashion so that they are functional and relatable to the components that you are labeling. So silk screen must be visible when printed onto PCB board. So the minimum size for most fabrication house will be a height of 35 mils and width or the legend width of 5 mils. So this is an ideal size where it's small enough to be printed on and it's legible enough to be able to read by consumers or end users. So if any smaller, what will happen is that these legends will end up as a very scrunch up silk screen, or because silk screen will be a pain, so it will not be good for anyone to read. Okay, next I will talk a little bit about the vias. So vias are holes that passes through the PCB layers to allow electrical connectivity between layers. So vias are made of 3 parts. So for those who are used to doing layout design, so I'm sure you know vias are actually quite critical in a layout design. So via is actually made up of barrel, pad, and anti-pad. Okay, there are many types of via available. You have the plated through hole, non-plated, as well as blind, buried, as well as dented and capped. So I'll just go through briefly. So for plated through hole, this is your typical or your traditional hole that you see on your board or those that you use on your layout design. For plated through hole gives you connection access to all layers. Okay, allows you to toggle from one layer to another with copper plating in the barrel, and it's actually easy to manufacture using standard drill bits, and it's actually relatively cost effective. I won't say cheap lah, because it depends on how many vias you use. For non-plated through hole, it's similar to your plated through hole but without the via barrel or the plating on the via barrel. So also cost effective, and it can be applied to one layer PCB board. And then for blind and varied via, they are also known as micro or laser via. So for micro or laser via, as the term suggests, they use laser. It's slightly more expensive. So, but their usage is very, there are advantages to the usage. So layers that are not using the blind or varied vias, you can actually utilize them to route or place any components. So you can actually maximize the space when you use blind or varied vias. Okay, so they can also be manufactured using drill bits, but of course extra processes is needed if you use the standard drill bits. Okay, and then for tented and cap, it's actually your normal plated through via with a covering on one end of the via. So the covering is usually the same material as your solder mask coating. So it's like a skin-like cover. So the advantage is to cover the via on one end to prevent solder blackpool or paste migration. Okay, so the typical use would be something like your IC. If let's say you have exposed thermal pad in center, and you do not want solder to actually run to the other side or backflow to the other side of the board. So you just want to keep solder in this area. So we add via centing to prevent any solder backflow. But the disadvantage is because it's exposed on one end, any contaminants can enter from this side. So can cause any potential issue on the via barrel or via placing itself. So if there's any possibility of the tenting that is incomplete or broken, again, the solder can actually flow towards the end. So, like I said, typically used with ICs for exposed large area on one end. And then for via plug, so via plug is actually the same as your plated through hole, but it has a filled barrel with either a non-conductive, that means like your solder mask material, or conductive material, that means a metallic material. Okay, this depends on your via usage and your design requirement. If you say you're designing a power board, you will need a conductive material in your via barrel. Okay, so the advantage of using a via plug is that it protects the via from exposure and contaminants. It prolongs your lifespan of your via, and then reduce all potential issues on wave soldering or any soldered issues. But the disadvantage is that you can't see your via. So any problems or any breakage in the via barrel is not visible. So it's harder for you to troubleshoot. Okay. Okay, so for tented cap and plug via, this is what you will see. I know it's a bit light here, but you can see there are some gray areas. Okay, this gray area is actually indicative of the location of vias meant for plugging process. So not all vias can be plugged. So normally, depending on the fabrication house, what they can actually perform via plug is actually for vias or drill holes that are lesser than 0.5 mm. So in terms of cost and the time, or the time taken to perform this vias, it's actually stated in this table here. For your plated through via, it's actually your typical via, so and it's actually quite cost effective. And plug is just similar, or tented is also similar, just an additional of either covering or filling. As for blind, varied, and stack via or via in pad, okay, this is actually just a hole or via on a pad. So this will actually take up more time as well as money to produce because of the extra processes involved. Okay, So I've covered on biotechnology. So just to let you know, there are a few courses that I am conducting, which are actually quite popular. So one of them will be the Gerber Techniques course, which is actually an expansion of what I have covered for the webinar today. So here I will cover skills and best practices in depth and to actually enhance your PCB design layout. And on top of that, I also do conduct basic PCB design course. And as this is actually a good course for those who are new to PCB layout design, for new grads or those who have minimal or no PCB design background. And of course, we do customized PCB design courses to cater to your needs. Okay, so just a little bit on Wizlogix, and we are actually a one-stop PCB solution provider. Our services include PCB layout design together with implementing good Gerber techniques and checking to ensure that manufacturing performance for timely delivery. We also provide full turnkey solutions for customers who require fabrication, component kitting, and assembly under one roof. And in addition, we do partner with several notable trainers as well as reputable training centers on technical competency courses. Do check our website or contact us for more details on our full range of PCB solutions. I hope that what I've shared today is beneficial in your line of work involving Gerber and Gerber techniques. Thank you everyone for joining me in this webinar today.
Thank you again for taking your time to join us today, everyone, and have a nice day ahead.